Hey everyone, and welcome. So today, we're going to tackle something we see all the time, right? A force that's, both a vital tool and a hugely destructive power, fire. Let's dive right into the chemistry behind that flickering flame.
Have you ever just stopped and wondered what fire really is? You see it in candles, campfires, your gas stove. But what's actually happening when something burns? What is that little flicker of a flame made of? Let's get to the bottom of this everyday mystery.
So at its core, fire is this process called combustion. Now, that sounds super technical, I know, but it's really just the sciencey word for, well, burning. It's a super fast chemical reaction between some substance and oxygen, and its signature move, releasing a ton of energy as heat and light.
Okay, so you can think about starting a fire kind of like you're following a recipe, a very specific recipe. And if you leave anything out, it just won't work. This recipe is famously known as the fire triangle.
So what are these three essential ingredients? First up, you need fuel. This is pretty simple. It's just anything that can burn. Think wood, gasoline, natural gas, you name it. Second, you gotta have oxygen, which, lucky for us, is pretty much everywhere in the air. And third, you need a source of heat to kick the whole reaction off. You absolutely have to have all three, no exceptions.
And this is actually a brilliant way to understand how we put fires out. See, firefighters don't just blast everything with water. They use different tricks to remove one side of this triangle. Water? That cools things down, taking away the heat. A fire blanket? It smothers the flames, which gets rid of the oxygen. And a fire break in a forest? That removes the fuel. You take away any one side and poof, no triangle, no fire.
All right, so we've got the recipe for starting a fire. But what is happening, chemically speaking, inside the flame itself? This brings us to a really key concept in chemistry.
Combustion is what we call an exothermic reaction. Exo means out, and thermic, well, that's about heat. So it's just a reaction that pushes energy out into its surroundings. You know that cozy warmth and the bright light you get from a campfire? That is the perfect picture of an exothermic reaction in action. You're literally feeling the energy being released.
Now, here's where it gets really interesting. Not all fires are created equal, not by a long shot. The kind of burn you get actually depends entirely on one critical ingredient from our fire triangle: how much oxygen is available. Okay, let's compare these two. On one side, you've got complete combustion. This is what happens when there's plenty of oxygen. Think of that clean blue flame on your gas stove. Then on the other side, you've got incomplete combustion. This happens when there's just not enough oxygen to go around. This is your classic smoky yellow campfire flame. And here's the crucial part, what they produce. A clean burn, it just gives you harmless carbon dioxide and water. But a dirty burn, well, it also gives you water, but it also creates carbon, that's the soot, and the really dangerous gas, carbon monoxide. And this is exactly why that distinction matters so much. That black stuff, the soot, it's messy, sure. But the real danger here is carbon monoxide, or CO. It's a toxic, poisonous gas that you can't see, you can't smell, which is why having properly ventilated heating systems and, of course, carbon monoxide detectors in your home is so incredibly important. Okay, so after the fire's out and the burning is done, what's left behind? Well, the substances that are created, we call them the products, they act like chemical fingerprints. They can tell us exactly what kind of fuel was being burned.
So the most common type of fuel we all use are called hydrocarbons. And hey, the name pretty much says it all. They're made of hydrogen and carbon atoms. Things like methane gas, the wax in a candle, even the wood in a fireplace, they're all hydrocarbons. And when they burn completely with enough oxygen, they always leave the same two fingerprints behind, carbon dioxide and water.
But what if your fuel isn't a hydrocarbon? What if you burn something like, say, a metal? It's a totally different process with a totally different result. When metals like magnesium or iron burn, they don't make carbon dioxide at all. Instead, they just combine with the oxygen from the air to form a new substance called a metal oxide. So if you burn a strip of magnesium, you're left with this white powder, which is magnesium oxide, a completely different chemical fingerprint.
So with all these different reactions, how do scientists keep track of it all? How do they describe the story of a fire in a clear, universal way? Well, they use the language of chemistry. Chemical equations. And let's take a quick look at how they're written, because it's not as scary as it looks.
It's actually super logical when you break it down. You start with your ingredients on the left-hand side. First, you list your fuel. Then you add what it reacts with, which for combustion is always oxygen.
Then, on the right side, you just write what was created, the products. So let's take the complete combustion of methane. Our fuel is methane. It reacts with oxygen. That little arrow in the middle just means turns into or produces. And the products, our chemical fingerprints, are carbon dioxide and water. See? Simple as that.
Okay, so that word equation is great and easy to read, but chemists, they need a universal shorthand. They need a way to write this reaction so that anyone, anywhere in the world can understand it precisely. So what they do is translate those words into chemical symbols.
And here it is. I know, it might look a little intimidating at first, but it's telling the exact same story. CH4 is just methane, O2 is oxygen, CO2 is carbon dioxide, and you probably know H2O is water. And those little numbers in front, they just tell us how many of each molecule are involved in the dance. You see, you can't just create or destroy atoms in a reaction, so these numbers make sure everything is balanced. It's the elegant, universal language for describing fire.
So there you have it. From the simple fire triangle to the chemical fingerprints left behind, we've kind of unpacked the science of combustion. I mean, fire is the exothermic reaction that has literally powered human civilization. But as we saw it, its most common product is carbon dioxide. And understanding this fundamental chemistry is really the first step to asking a massive question for our future. How do we balance the incredible power of the flame with the impact of what it leaves behind? That's definitely something to think about. Thanks for tuning in.